Friends, we would like to find the relation between Young's modulus and modulus of rigidity. So for that, we shall be considering a diagonal AC. So we shall be subjecting this block ABCD to a shear stress on this particular face. So there will be complementary shear stress formation on all four faces of this particular block. Now, due to application of this shear stress, there will be a linear strain produced in the diagonal AC. We shall find out the linear strain in the diagonal AC with the help of geometry, and we will also find out the linear strain in the diagonal AC with the help of generalized Hooke's law, and both we will equate. So I'll show you how we are going to proceed. So let's say we have applied the shear stress on this particular face. So there will be deformation of the block like this. A will be displaced to point A dash and D will be displaced to point D dash. So this angle is called as phi. So this angle is also called as shear strain. I have already explained in the previous videos that how this angle is called as shear strain. Okay. So when you apply shear stress on this particular face, so there will be formation of complementary shear stresses all along the four faces of the block, as I have shown in this particular figure. Now, so in order to get the relation between Young's modulus and the modulus of rigidity, we shall find out the linear strain in the diagonal AC. Okay. So initially we shall find out the linear strain in the diagonal AC with the help of geometry. So there is one very important assumption that the deformation is very small. Okay. Since the deformation is very small, this AA dash is going to be extremely small. So that is very important assumption, friends. So we are going to assume very small deformation. So when we assume very small deformation, it means AA dash, this particular displacement is going to be very small. So now I'll draw a perpendicular from point A on this particular diagonal. It will look like this, friends. So let's say we have drawn a perpendicular here. This is going to be perpendicular, friends. So since the deformation is very small, AA dash is very small, so we can say that A dash E is also going to be very small. Okay. So therefore I can write down that A dash E, that is this distance. Okay. So this indicates the elongation in the diagonal. So AA dash is also very small. Since AA dash is very small, so we got A dash E is very small, friends. Since A dash E is very small, we can also write down that A dash E is approximately equal to AE. Okay. So that is also very important outcome. This is only valid in case of small deformation. So I can say that A dash E is approximately equal to AE. So when A dash E is approximately equal to AE for a small deformation, so we can also conclude that this angle and this angle are 45 degrees each. Okay. This is also going to be 45 degree and this is also going to be 45 degree. Now, so from basic geometry, we can easily write down that this side, that is A dash A, is going to be root 2 times A dash E. That's very simple because these two sides are equal, because these two angles are equal, right? So I can easily find out, if I use Pythagoras theorem, I can easily prove that this A dash A will be root 2 times of A dash E. Now remember, friends, we wanted to find out, as I have already told you, we wanted to find out the elongation in the diagonal. One more thing I want to tell you here, since this is very small, so this side, that is EC, is also approximately equal to what? AC. So this side is approximately equal to this side. Both are diagonal, friends. Okay. So we can also write down the length EC is approximately equal to length AC, which is the original length of diagonal. So these are the outcomes due to the assumption that the deformation is very small, right? So now what we shall do is, first we'll find out the strain in the diagonal AC with the help of geometry. So let's do that first. Therefore strain, linear strain in the diagonal. So I'm taking diagonal AC, friends. That was the initial condition. So that is equal to, that is change in length upon original length. So what is change in length, friends? If you see that this diagonal AC was initially like this, due to application of shear stress, it has become A dash C. Okay. So I can say A dash E is the elongation and then EC is the original length. So we can say divide by EC, as you can see from the diagram itself. Okay. So this much portion is the elongation and this is the original length, we can say, because EC is approximately equal to AC. So I can also write down here A dash E divide by AC, because divide by AC, because EC is approximately equal to AC. So this is what we got. The linear strain in diagonal AC is this much, right? So we have got, friends, A dash A equals root 2 times of A dash E, right? So from here I can write down, friends, A dash E equals to A dash A divided by root 2. So I'm going to put that particular expression over here. So you will be getting the linear strain diagonal AC will be A dash A by root 2 times AC. So I got the expression for linear strain the diagonal AC. Now if you see here, friends, in this triangle ABC, this is 90 degree, friends, and this is a diagonal, right? So this is a square block I have taken. So this is 45 degree, as we know that 45 degrees. This is also 45 degree, friends, right? So I can easily write down that diagonal AC will be equal to root 2 times of AB. Okay. So instead of this AC, what I have here, I can write down what? Root 2 times of AB just from geometry itself, right? So if I do that, linear strain in diagonal AC will be A dash A divided by root 2 into AC is basically what, friends? AC is root 2 times AB. So root 2 times AB, fine. So if you simplify this, you will be getting A dash A by 2 AB. Okay. So the linear strain in diagonal AC is nothing but A dash A by 2 AB. So we have already discussed earlier that for the shear strain phi is the ratio of lateral displacement, that is A dash A, of the layer divided by its distance from fixed layer, that is AB. Okay, so this already we have discussed earlier. So shear strain phi, which is this, is nothing but A dash A by AB. So this A dash A by AB is nothing but phi. So from here you will get this A dash A by AB is going to be phi. So it will be, friends, phi by 2. So I got linear strain diagonal AC is nothing but shear strain phi divided by 2. We can further simplify this because we know that the shear strain is nothing but shear stress divided by modulus of rigidity. Okay, by Hooke's law. This already we know. Okay. So this also can be simplified further. So I'll get the final expression as linear strain in diagonal AC is nothing but, instead of phi, I'll write down shear stress by G. So we'll get shear stress by, and 2 is here, 2G. This is the first expression I got, friends. Very simple expression. Okay. So I got linear strain in diagonal AC with the help of geometry as shear stress divided by 2G. G is called as modulus of rigidity. Okay. This is one way of finding out the linear strain in the diagonal. Now, I can also find out linear strain with the help of generalized Hooke's law. So, let me show you that part also. Now, we know that if you apply shear stress over here, so you will get complementary shear stresses all over the faces. This diagonal will have a stress acting like this in the tensile direction and the stress acting like this in the compressive direction. So, I want to find linear strain in this diagonal. Okay. So, I am going to use generalized Hooke's law. So I want to find strain in this particular diagonal, that is diagonal AC, because shear stress tau is acting in this direction. So this will call a strain in this direction, that is given by tau by Young's modulus, and this is compressive. The compressive stress is also helping for this particular elongation or this particular strain. So it is going to be plus Poisson's ratio times shear stress divided by Young's modulus. So if you simplify this, this is going to be shear stress by E divided by 1 plus mu. So now this is what we got. So this is our equation number 2. So from equation 1 and 2, this is also linear strain in diagonal and this is also linear strain in diagonal. So both are going to be equal. Okay. So we are going to equate them. This equation 1 and equation 2, both these equations represents linear strain in diagonal AC. So we can equate this equation 1 and 2. So from equation 1 and 2 we can write down, we shall be getting this, that is shear stress by 2G will be same as this one, that is shear stress by Young's modulus times 1 plus mu. So if you see here, you can easily cancel out this numerator from both sides. So we'll get 1 upon 2G equal to 1 upon E into 1 plus mu. So if you simplify this, you'll be getting Young's modulus equals 2 times modulus of rigidity 1 plus mu. So this is the relationship between Young's modulus and the modulus of rigidity. So let me again explain the entire thing. We shall be finding out the strain in the diagonal AC with the help of geometry. This is the elongation, that is A dash E is the elongation and EC is the original length. So A dash E divided by EC is the strain in the diagonal AC. That is what I have written here, A dash E by EC. But EC is same as AC because the deformation is very small. So we got A dash E divided by AC. Since the deformation is very small, then this length will be approximately equal to this length. So both these angles are going to 45 degree. So A dash A will be root 2 times of A dash E. So we have A dash A equal to root 2 A dash E. So we will get A dash E equal to A dash A divided by root 2. That is what I have written here. Okay. So instead of A dash E, we can write down A dash A divided by root 2 and AC is as it is. Now again AC, friends, if you look at here AC, so this is basically diagonal and these angles are 45 degree. So AC is nothing but root 2 times this side AB. So that I have put root 2 times AB. So root 2 into root 2 becomes 2. So we got A dash A divided by 2 AB. Okay. Now A dash A by AB, that is the lateral displacement and that is distance of that particular layer from the fixed layer. So A dash A by AB is nothing but shear strain. So we got this value A dash A by AB shear strain, that is phi, this angle. So we got phi by 2, but shear strain is nothing but shear stress divided by modulus of rigidity. So instead of phi I have put shear stress by G. So we got shear stress by 2G as the expression for linear strain in the diagonal AC. This is by geometry we got, and with the help of generalized Hooke's law, along this diagonal there is a tensile stress acting and along this diagonal there is a compressive stress acting. So strain in this direction will be stress divided by Young's modulus, that is this, and this also will contribute towards the strain in this direction. So that is plus Poisson's ratio times this stress divided by Young's modulus. So if you take shear stress divided by E common, we will get 1 plus mu. So equation 1 and this equation 2, we can equate these two equations because both of them are representing the linear strain in the diagonal AC. Okay, so if you equate them, shear stress part will be cancelled out. So we will get 1 upon 2G equals 1 upon E 1 plus mu, and if you simplify this, you will get Young's modulus equal to 2G into 1 plus mu. So this is the relationship between Young's modulus and modulus of rigidity.